Okay, I think we'll get started slowly. So my name is Chloe, and it's my very great pleasure to be hosting tonight's joint meetup between two WiMLDS communities, the WiMLDS in Dakar and the other in Paris. So it's too bad that because of the pandemic, it's difficult to have in-person meetups, but we're compensating that by having joint online meetups, and it's very nice to be able to meet the two communities. So I'll start with a little introduction. So first of all, I wanted to remind you, those of you who have been to WiMLDS events before know it, but we do have a code of conduct. Basically, the code of conduct says, please don't be an asshole and just be kind to others. So we're hoping to provide a harassment-free experience for everyone. So the idea is try not to make other people uncomfortable, try to be kind, try to behave as professionals. Because we are having this meeting online, we have a few additional rules in the code of conduct. In essence, we'll ask you to switch off your videos unless you're the one talking, so as to save bandwidth. And of course, to mute your microphone when you're not speaking. If you want to ask a question, please use the chat or raise your hand, and we will ask you to unmute, or we will read your question if you wrote it in the chat. And don't worry, if we get disconnected, we will all calmly reconnect to the same Zoom link. All right, so why are we here tonight? We're here as part of WiMLDS, Women in Machine Learning and Data Science. Our mission is to support and promote women and gender minorities in machine learning and data science. So this goes from people who are interested in the field or studying it to people who are active practitioners. WiMLDS is a large community. It has over 100 chapters, I just checked yesterday, in more than 30 countries and over almost 66,000 members all over the world. And among two of those chapters are the one in Paris and the one in Dakar. So tonight's agenda, once I'm done giving this introduction, is that we're going to have two talks. One from Azade Farshad from the TU in Munich, and the other by Sokhar Samb, who's data scientist at TULX. And then hopefully we'll have a bit of time left over for quick interactive sessions to ask more questions and chat a little more. So I'm going to say a few words about WiMLDS Paris, which I'm representing tonight. So I'm the one talking, but this meetup wouldn't have happened without my three other co-organizers, Caroline, Marie, and Nathalie. We were founded in 2017, so it's been a while now, with the third largest WiMLDS chapter in the world, and we're very happy of the success we're having with this community. There is one announcement I have that is specific to the Paris WiMLDS community, which is about our next event. I'm very happy to announce, you're hearing it here for the first time tonight, that we're going to join forces with Scikit-learn people to host a Scikit-learn sprint on March 12, and it's going to be hosted by Cyber Angel. It's going to be in person in Paris, and you should have more details about this in a few days. So I'm going to now let the mic to someone from the WiMLDS Dakar community, Mariama, if you want to say a few words about your meetup.
Okay, thank you very much, Chloe. So hi, everyone, and thank you for all of you for joining us today. So we are happy to organize this meetup joint with the Paris team. So I'm going to just do a quick presentation of the WiMLDS Dakar. So far, you can say that the WiMLDS Dakar was created in August 2020 with 4 co-organizers, and we are also present on social medias like Twitter, Facebook, LinkedIn at WiMLDS Dakar. So the 4 co-organizers who created WiMLDS Dakar are me, Maria Madravi, she is currently a PhD student working on AI and agriculture. There is also Aisa Tundoy, so she's not here today. She's also a machine learning engineer. There is also Aisa Tupai, who was which is working at the Orange Middle East Africa, and Sokhar Samb is going to do the presentation on low resource languages, machine translation today. So far we have organized it 4 meetups. The first one was the lunch. The second one was for NLP datasets presented by Julia, which is at Google, and Selina, which is the CEO of Zindi. So the third one was on AI and ethics, organized with P and AI, deep learning.ai, with Bellona Sona. And the fourth one was during the Indaba X Senegal. So we also co-organized the Indaba X Senegal with Galsen AI and did tutorials inside. So far that's all for the WiMLDS Dakar. And thank you. So we'll let you, Chloe, to continue for today, and Sokhar will do the presentation after.
Thank you very much, Mariama, for this presentation. So I'm almost over. We can almost move on to the technical stuff. So we also present on Twitter and LinkedIn and Medium and many other places. You'll find us online, whether the Paris or the Dakar community. If you want to tweet tonight, you can use the WiMLDS and WiMLDS online hashtags, and you can tag WiMLDS Paris, that's us, and WiMLDS Dakar, it's Dakar. And now we can get started. So I'm really happy to welcome our first speaker for tonight, Azade Farshad, who is a research scientist at the Technical University in Munich, and who is going to tell us about meta-image generations using scene graphs. So Azade, I'm going to unshare and let you share your screen.
Thank you for the nice introduction, Chloe. Now I will start sharing my screen. So you see my screen, right?
All right, we do see your screen.
Okay, then I will start. Hello, everyone. My name is Azade Farshad, and I am a 4th-year PhD student and researcher at Technical University of Munich. In this talk, I am going to present the work of me and my colleagues on few-shot image generation from scene graphs, which was accepted at PMBC Conference 2021. So why do we need few-shot image generation? Around 3 years ago, there was a paper for a generation of images from scene graphs, which I will later talk about in detail. Unlike image classification and object detection tasks, there are very few data sets of paired scene graph and image data. And as you can see here, the quality of the generated images are not good. So what is the solution? We propose to use meta-learning to learn a model that generalizes better to new scenes. So we train the model in an episodic fashion, and the episodes are based on the specific scene characteristics. Using this approach, we are able to generate images which look more realistic than the baseline. So what are semantic scene graphs? Scene graphs are, as their name suggests, graphs that describe a scene. To the right, you can see an example of a scene graph. The nodes in the graph define the objects in the scene, and the edges are the relationships between the objects. For example, here to the right, man and t-shirts would be the objects in our scene, and the relationship between them, which is varying, is the relationship or edges of our graph. So the relationships can be actions such as holding, eating, or riding. They can also define the relative positions of two objects, for example, near, left of, or above, and etc. The graphs can also include object attributes such as color, shape, or material. Scene graphs are very useful and important representations because they can connect the semantical world of natural language to the computer vision world. Semantic scene graphs have been used in different applications. Most of the papers in recent years have been focusing on prediction of scene graphs from images, which usually happens by combining an object detection model such as faster CNN and relationship prediction. Other applications are generation and manipulation of images using scene graphs or unconditional generation of scene graphs. To generate an image from a scene graph, one first needs to process the scene graph using a graph neural network or a graph convolutional network to generate features for objects in the scene. These features are then used to predict the bounding box for each object and the segmentation mask. These are used to construct the scene layout. The final image is generated by a generative adversarial network or GAN conditioned on the constructed scene layout. To perform few-shot image generation, we use meta-learning. Meta-learning is an optimization-based approach for few-shot learning. Usually, the model is trained on different sets of tasks with few samples of data. Each task consists of a support set which the model is trained on and the query set which the model is tested on during our training or meta-training. The query set works similar to a validation set. Usually in meta-learning, the model is optimized based on its performance on the query set. A well-known meta-learning approach is MAML or model-agnostic meta-learning, which is based on second-order optimization and is therefore computationally expensive. To overcome this issue, Reptile proposed a simplified first-order meta-learning approach by training different models on different tasks and then averaging these models. In each iteration, a set of n tasks are randomly sampled. The model weights are computed by performing a stochastic gradient descent on each sampled task for k steps. Finally, the meta-model parameters, which is denoted by theta here, is computed by averaging the weights obtained from each task. Our proposed approach has 3 steps: task construction, meta-training, and fine-tuning. The tasks are constructed by dividing the dataset based on the scene attributes. The attributes can be labeled features from the dataset. For example, for Berkeley Deep Drive dataset, we use the attributes such as time of the day or the location. For Action Genome, which is a dataset of video sequences, each specific video sequence is considered a task, and for Visual Genome, which doesn't have labeled scene attributes, we cluster the dataset using a scan. The meta-training is done by optimizing the model on randomly selected tasks. The model parameters are updated in each meta-epoch by averaging the parameters of the trained model on the sampled tasks. The fine-tuning step is done by fine-tuning the model with the pre-trained weights on the support set of the test data and testing on the query set. Since our method is built on top of the scene graph to image from Johnson et al., I am going to first explain this method in detail. The input to our model is a scene graph. The scene graph is defined as a set of triplets of object, predicate, and subjects. For example, each such triplet would be person sitting on sofa. These triplets are defined by their assigned labels from a vocabulary set. The numerical labels are then fed to an embedding layer to get features for the elements in the graph. After getting the features for our graphs, these are then fed to a graph convolutional network or GCN. The GCN then provides us with processed features for all the objects in the scene. These object features are then used to predict the position of the objects and the corresponding segmentation mask. The layout is constructed by positioning the masks in the predicted bounding box position. So the layout can be also seen as a segmentation map, but multi-dimensional. So instead of having the dimension of our layout as the number of labels in normal semantic segmentation task, it is the dimension is based on the number of features that each of our objects have. The image is then generated by the Cascaded Refinement Network or CRN from the constructed scene layout. The CRN has a generative adversarial structure, so we also have discriminators which classify if the generated image is real or fake. In the bottom, you can see the objective functions used in this work. The first term is the bounding box regression loss, which is a simple L1 loss between the predicted bounding boxes and the ground truth bounding box. The GAN objective is applied to the whole image as well as each generated object separately, which is defined as L of GAN obj and L of GAN global here. We have also an auxiliary classification loss, which tries to classify the generated objects in the scene. In the end, we have a perceptual loss that verifies if the features generated from our fake images are realistic, and then image reconstruction loss to increase the quality of the generated images. In our framework, we have a training and a testing phase. We start by randomly selecting tasks during our training. The task construction is done as a pre-processing step, which I explained before. In each meta epoch, we train this SG2IM model on a sampled random task, K, to get the learned model weights. Then we update the meta model parameters by averaging the weights of all the models in our meta epoch. Using this episodic training, our network learns a model that adapts fast to new data. After the training is done, we take our meta-trained model and test it on the scenes that have not been seen before. This is done by fine-tuning the model on very few samples from the scene with the new characteristics. To give an example, our model is trained on scenes belonging to a set of specific times of the day, for example, night and dusk, or specific locations such as highway. Then in the testing phase, our model is trained with just 5 samples of day images in the city street, and it's able to generate higher quality images in the new scene. We report the qualitative and quantitative results of our work compared to the baseline on 3 datasets. These datasets are Visual Genome, Berkeley Deep Drive, and Action Genome. Visual Genome is a dataset of images and semantic scene graphs with diverse objects. Since this dataset doesn't have labeled scene attributes, we cluster the data into 100 clusters using SCAN, which is a self-supervised clustering approach and is pre-trained on ImageNet. We use 60 tasks for training or meta-training and test on the remaining 40 tasks. Berkeley Deep Drive is a street view dataset. We split this dataset based on the annotated scene attributes, which gives us 23 tasks in total. Again, we use 20 tasks for training the model and evaluate it on 3 tasks. Since Berkeley Deep Drive does not contain scene graphs associated with images, we construct spatial scene graphs automatically using the ground truth bounding boxes, which leads to 6 spatial relationships, which are left of, right of, above, below, inside, and surrounding. We also evaluate our model and action genome dataset, which turned out to be a very difficult dataset for image generation. The action genome dataset is originally designed for human-object interaction. Therefore, only the objects which the human interacts with are annotated in the scene graph. Here you can see an example of the action genome dataset. This dataset consists of over 700 video sequences, and we split the tasks based on the scene sequences. So 90% of the videos are used for training, and the remaining 10% is used for testing. Each task here is all the video frames belonging to the same video sequence. It's not possible to present all the images generated in image generation works, and people may cherry pick the images with higher quality images. So it's important to have a quantitative metric for image generation. To quantitatively evaluate our method, we test our model and baselines using the FID and KID metrics. FID, or Farshad inception distance, uses a pre-trained inception model on ImageNet to compare the quality of the generated images versus real images. FID does this by first feeding both the generated and real images into the inception network. It then estimates the distance between the feature vectors of generated and real images by mapping them to a continuous multivariate Gaussian distribution. The distance is computed using the Wasserstein metric between the two Gaussians. This metric quantifies the quality of the generated images. Lower FID scores show that the images have a higher quality since their distance to the real data distribution is less. The second metric that we used is KID, or kernel inception distance. The KID again uses a pre-trained inception network to obtain feature representations from the fake and real images. But it calculates the squared MMD, or maximum mean discrepancy, between the inception feature representations as a dissimilarity measure between the two probability distributions. Since KID doesn't assume an underlying data distribution, it is less biased and more reliable than FID. So here you can see the results of our experiments on Berkeley Deep Drive dataset. In the top, you can see some examples of generated images in different scenes. We compare our model to the original SG2IM on different shot values. The shot value means that after method training our model, in the test phase, we fine-tune it on different numbers of shots from new scenes. For example, in the first column, we have 160 shots, 15, in the second column, we have 10 shots, and then in the last column, we have 5 shots. So the pre-trained model is fine-tuned just on 160 or 5 samples from the new scene that has not been used for training the model. As you can see, our proposed model that uses meta-learning is able to perform better in all of the settings with different shot values. So we also tried using a different decoder than the original cascaded refinement network, which is the SPADE network. And as you can see, based on the metrics provided, the SPADE provides much higher quality images than the original CRN network. Here, again, you can see some qualitative results of a specific scene graph and the generated images. On the top, you can see the ground truth scene graph used for generating the images, and on top right, you can see the ground truth image that was originally assigned to this scene graph. And as you can see, the CRN and both the original SG2IM have artifacts and low quality image. And on the other side, in the last column, Mix provides the best quality images. As I mentioned, the Action Genome dataset is a very challenging dataset to generate images from, and we suspect that this is probably because of the missing annotations on objects that are not, that the human is not interacting with. And here you can see that despite the difficulty of the generation of images, at least our proposed method performs better, but still this is a challenging task. And here you can see the results of the few-shot image generation on visual genome dataset. And as I mentioned, the data is clustered on this dataset because it doesn't have the scene attributes annotations. And we see that, again, the proposed mixed model is able to outperform the original scene graph to image, both quantitatively and qualitatively, in different settings with as few as 5 samples from similar scenes. And to conclude the talk, we saw that meta-learning can enable training image generation models in new scenes with as few as 5 samples. We also showed that the meta-trained model provides a better initialization even when the model is trained with higher number of shots, such as 160 samples. The proposed method is able to outperform the state-of-the-art in image generation using scene graphs, and is the first work for few-shot generation of scenes in the wild. However, despite the current improvements, generation of images from scene graphs is a challenging task, especially in higher resolution image generation. So there is still a long way to go and a lot of room for research in this topic. And thank you for your attention. This is the end of my talk, and I'm looking forward to your questions.
All right, thank you very much, Azade, for your talk. So are there any questions? So feel free to either to put a message in the chat or raise your hand. Yes, Mariama, if you want to unmute and ask your question.
Okay, so thank you, Azad, for the talk, for the great talk. So my question is like, in your approach, you said you used an average of the models that you train it on different tasks. So I was asking why you take the average, maybe why you didn't use a weighted of the different model based on their performance on the different tasks that you train it.
So let me go to the slides that you mentioned. So we adapted the reptile network that you can see here, which also takes the average of the models because it's a very simple few-shot learning approach. It can achieve similar performance and computing the performance of the model on the query set and taking the second order derivative, which was the mammal work. And so the scene graph to image work is very complicated, and it's by itself, it takes 3 days, for example, to train on the visual genome data set. And by adding an extra second order derivative that may not optimize as well, so the performance is similar, it would make the computational even more expensive. So this is a very simple approach, but I agree that the simple averaging may not be enough. So especially in one of our other works, we looked into taking for example, the importance of other works, other tasks into the that formula rather than just averaging and giving more importance to some other specific tasks. Did I answer your question?
Yes, thank you.
No problem.
So based on your experience with images, do you think that scene graphs can be applied to other types of data like text or others?
So which one? You mean like few-shot generation of text or?
Yes, like using this scene graphs.
I'm not sure. So you want the scene graph itself is actually text, and we want to take it from the text modality to image modality. But what do you mean by the generation of text?
Just like the way you use it with images. Can we, for example, use it on text or other types of data which are not images?
I think it's possible. So, but for that, I wouldn't suggest few-shot learning because I think there are lots of text data. So maybe just simple generation methods that, for example, here that you can see that from noise, we construct a scene graph. So this is just text without any images. So these kind of works may perform better than using few-shot learning, I would say.
Okay, thank you.
No problem.
Great, thank you. I see another question in the chat. So did you notice situations where your proposed models are working better? I actually had the same question myself. But Marie asks, I guess you can't compare the metrics computed on a model trained about street with metrics computed in a model trained about animals. So I guess it's 2 questions in one, but yeah. So you mean the metrics used for evaluating the quality of the generated images?
Oh, yeah.
Yes. Oh, go ahead, Marie.
The thing is, the FID and KID compare the distribution of real data and the generated data on the same data set. So it's not the thing that we compare street view images to other kind of like scenes in the wild, but it just compares the distributions of real street view data to the distribution of generated street view data.
Yes, so your metrics depend on your data set, exact? If I
Yes.
So you can compare like situation, and you can't use your metrics to objectify the performance on some kind of situation and some others.
Yes, exactly. But again, the inception network that is used for both of these metrics is pre-trained on ImageNet, but we can consider that ImageNet, which is a very large data set with millions of images and 1,000 classes, covers many of the object types.
Yeah, like you can say you have everything.
Yes. But still, if you submit a paper for image generation, the reviewers may ask for human user study. So that is also another reliable kind of metric for quality of generated images.
Okay, thank you.
No problem.
Great, thank you. Let's see. So for now, I'm not seeing any other questions, so I will ask one of my own, which is, I mean, it's going a bit further on the questions that was already asked to situations where your proposed models would be working better. Do you have any insight on what kind of scene or scenes are easier to learn than others?
Sure, yes. So I can for sure say that there are some scenes that are very difficult. For example, human faces, even though there are some GANs that when they are only trained on human faces, they work perfectly. But when they are combined with the scenes in the wild, they fail. But for example, some easy objects are usually animals because they usually look the same in all the scenes. For example, elephants. So those were the most simple things that I saw that were to generate.
All right, so we'll remember that elephants are easier to learn. So thank you very much, Azade. We still have a few minutes if someone wants to ask an additional question. So you can raise your hand, or at this point you can even unmute yourself and just ask your question. And if not, well, I'll thank you again, Azade. It was a very interesting talk, and thank you for participating from Munich. So adding one city to our Paris-Dakar event. So then I can invite our second speaker for tonight, Sokhar Samb, to come up here and share her slides.
Thank you very much. Okay, so let me just share my screen. Oops. Yes. Okay. Okay. Right. So can you see my screen?
Yes, thank you.
Yes. All right. Thank you. So thank you, everyone, and thank you very much for organizing this. We are very happy to be here today and discuss about machine learning. And in this talk, we're gonna just talk about low resistance machine translations. So this presentation is made by the WiMLDS, and this is a work that is still going on. So we are still working on this, but we think that it's interesting to discuss about it and see. All right, so let me just give us quick definitions. So, you know, natural language processing is a field of machine translation, which is actually have many area like text generations, you know, question and answering. All these are neural machine translation methods. And actually, natural language processing, I mean, and actually what we want to do here is that we are interested in the machine translation method. What does machine translation mean? So machine translation mean like we have source languages, and then we want to translate this to a target language. So in this case, we are using the case of English to Wolof. So English, everyone knows English maybe here, but Wolof maybe not. So Wolof is the most spoken language in Senegal. And so, you know, our official language is French, but not everyone speaks French in Senegal, but almost everyone speaks Wolof in Senegal. So we think that it's interesting today to have a method that will help to translate Wolof to English or English to Wolof, and this will make communication easier. But what we realize is that Wolof is part of what is called low resources. And almost all the African languages are part of the low resources. And what does low resources mean is that those languages that do not have many parallel corpus to be translated. So we realize that in the world we have like around 7,000 languages, but only 20 languages are like they have resources to be trained for a machine translation model. So it means that to be able to translate Wolof into English using machine translation, we need to have some methods for data augmentation to create more data to improve the machine translations model for Wolof. All right. Okay, so in this work, so we just use a method which is called back translations. We will see later what the back translation means, but this is the method of data augmentation we're using in this case to generate what is called synthetic data. And these synthetic data are going to be added into the existing parallel corpus in Wolof to make a machine translation better and improve maybe the result. Okay, so our data. So we have here a sample of data that is called, well, this is what is called parallel corpus. So it means you have sentence from a source languages and the corresponding translation from a target languages. And this is a sentence into Wolof, and here is the corresponding translation into English. So this data is from what is called the GW300. And this GW300, it has over 300 languages, around 100,000, right? And actually Wolof is part of the existing data in the GW300. But this data is only the translation of the Bible. We have only the translation of the Bible in this data and the NYOM data from the Ubuntu. So here we collected from the GW100 around 17,045 parallel sentences. Okay, and then we add the existing NYOM data, which is just around 200. And this is the existing parallel corpus we have into Wolof, which is, as you can see, very small for machine translation. Okay, so we try to use what is called monolingual data. And this monolingual data is just like you have sentences from given languages, but you do not have the translation. So this is what is called monolingual data. And this is what we use to make a data augmentation to improve the models. All right, so here, so just to present a quick, the model we're using here is that what is called the JOY NMT model, JOY Neural Machine Translation Model. And this is based on PyTorch. It is designed for novice. So it's a learning machine translation, which is created by Julia from the Masakani group. And this model, what is interesting is it can be used with the architecture of recurrent neural network, but also with the architecture of transformer. In our case, we are using it with transformer, okay, and with the beam search, okay. And this is actually what we're gonna use for our translation models. And this is like a bit the image of the transformer. And in this case, we are using what is called the multi-head transformer, the multi-head attention. So the multi-head attention is that just attention mechanism that is run through it several times.
I think is, but her battery is off. Her laptop is off. I saw it was. Sorry.
Okay. So Sokhar is still online, but we've lost her.
Okay. So sorry. All right. Okay, so sorry once again for this.
All right. Very good.
All right,
We'll
so
leave you to it now.
thank you. Okay, so here I was discussing about the data we're using for machine translations. So as I said, we have like around 17,000 data, what is called parallel corpus, and this is represented on this way. You have sentences from the source language and the translation or corresponding translation from the target language. And this is what is called parallel corpus. And we have this data from the GW300, but this is like very small for machine translation models. So here we try to use a data augmentation method to make this like to have more parallel corpus for better translations. Okay, and this is the model we use. So I was saying that the interesting thing in this is that we can have an architecture using the recurrent neural networks, but we can also use the transformer. And in this work, we are using the multi-head attention, which is a transformer mechanism that runs through it several times. And the output from the independent models is like concatenated to create just one output. And this is the architecture of the multi-head attentions. And in our case, we are using a 4-head. So you can have many heads as you want, but in this case, we are using just a 4-head attention for our translation. Okay, so what is the techniques we are using here? As I said, I talked about back translation. What does back translation mean? So here we are interested to make a model that will translate from English to Wolof, right? So this is our initial models. But we don't have enough data. We want to create what is called synthetic data that we're gonna add to our data from the GW300 that we already discussed about. So what do? What we do is we create an inverse models. So our first model was from English to Wolof. So we create an inverse model, which is translating from Wolof to English. And we scrap what is called monolingual data, which are data that do not have translation. So only Wolof data, they do not have translation to English. And we use this, we translate this monolingual data with our back translation models. So from Wolof to English. So we're gonna give the monolingual sentences Wolof, to our model that will translate them to English. So this will create a new parallel corpus, right, from Wolof to English. But this translation sometimes is, we already say that the model is not actually performing well because we do not have a lot of data, which means when we do we create the back translation models and then we do the translation, we may not have a good result from the translation. So we need to create some methods to select the better sentences from this translation. And this is where we use what is called the cosine similarity. So what a cosine similarity means? Cosine similarity is a mathematical concept which is making a comparison between two vectors. So you have two vectors, you want to evaluate what is the similarity between the two vectors. So as you know, when you have a sentence, this sentence is represented with a vector. So you have a Wolof vectors and the English vectors. What you want is, or you have two Wolof vectors and you want to check what is the similarity between, is it really the same thing or not? So let me just show you how we do that. So first of all, we have the monolingual data, and this monolingual data is sent to the back translation models. So this back translation model, we translate this and then create with the monolingual data parallel corpus. Okay, and this parallel corpus, we check the similarity between the translated Wolof data and the initial monolingual data using the cosine similarity. Okay, so what it means is that when we translate the monolingual sentences, which is Wolof, we translate it to English. This English is also sent to the initial translation model, which is translating from English to Wolof. And then it will generate again Wolof sentences, right? So we will check the similarity between the monolingual sentences, the initial one that we scrapped from website, and the one that is translated from the synthetic data, right? And then we check the similarity between this. And what we did is that we consider, how do I say it? We consider as what is called, like, we consider that all the sentences that has a similarity greater than 50%, we consider that this has a good translation. So this, the 50% is just something that we choose because when we choose higher than 50%, we may lose all the monolingual data we have because actually the translation we're having is not really perfect. So we need to make this threshold very small to have some sentences. Okay. So, and this creates what is called synthetic parallel corpus. And this synthetic parallel corpus is added to the initial parallel corpus we got from the GW300 to create now our new data set for translation. Okay, so, oops, yes. So let's see how this is performing, or how this is increasing the score of our models. So initially, when we train the model without the synthetic data, which means only the data coming from the GW300, we had a blue score, which is 27.55. Okay, so this is the blue score is like actually the score we are using to test the performance of our model. And this is what is called the perplexity. And we have a perplexity of 6.8 from the model without the synthetic data. So when we add the synthetic data, we obtain like a blue score of 31.8, which is increasing, and the perplexity that is decreasing, because the perplexity is a kind of an error, so it's decreasing to 6.5. So which means, and this is the loss that we're having, and this is interesting because we realized that when we created synthetic data, we were able now to increase the performance of our model from 27 to 31, which is not bad. So, and this actually is one technique of data augmentation for machine translation. So we may encounter, like we may use many other different methods for translation, but we consider that this is a very easy way, and it's helped actually to increase the performance of our model. Okay, so here, so like I said, we use one method of data augmentation, which is the back translation. So downloading monolingual data to create a new data set with the initial data with the GW300. So the problem we have with this method is that actually, as we know, the data that we have from the GW300 is data coming from the Bible. So we have only data coming from the Bible, and also the monolingual data we got, many of them are related to religion. So which means we have what is called the domain mismatch, because all the data we have are almost concentrated to one topic. So imagine now you have a sentence which is very different from religion that you want to translate with this model. You may have a very wrong translation because your models, the vocabulary of your model is around religion. So this is one problem that we are still working on to see how to go over these ones. But at least we were able, with the back translation method, we were able to improve the model from 27 to 31, which is interesting. And so this means that when if we are able now to create more data, to scrap more monolingual data with a better monolingual data, we could have a model that will perform very well. And one thing I wanted to mention is also the problem with the monolingual data is that we have, actually to find data that is very well wolof is very difficult. So most of the monolingual sentences that you will have they have a mix of wolof, mix of French inside, Arabic sometimes inside, which is not like helping the model to improve. So these are some problems that we could see with these techniques, but it's actually improving, and then we are still like doing like the work to try to find more monolingual data, because creating someone may say that what if when you create your own data, but data creation is very expensive, because when you want to create your own parallel data, you need to pay people to make the translation, right? So it's time consuming and very expensive. That's why it's now interesting to focus on some methods, some data augmentation method that can help the model to improve without time consuming and spending a lot of money on it. So thank you very much for your attention. If you have any questions.
Thank you very much for your talk, and especially this difficult technical setup.
Sure.
So we'll take questions for Sokhar now. So if you have questions, please feel free to write them in the chat or to raise your hand. So we have a first question in the chat from Philippe, who is asking, so he says, I understand that you use a monolingual corpus in Wolof. Do you also use a monolingual corpus in English?
Okay, yeah, that's a great question, because actually it's interesting because, but now actually we're just using monolingual data from the wolof monolingual data, because our initial model is actually translating from English to wolof, you see. So if you use monolingual data, you want to translate it into wolof to make a back translation, which means you will use your initial model to do the translation. So that's why we're not using monolingual data, the English monolingual data. We are just using the Wolof monolingual data because we want to do a back translation.
All right, thank you. So I had a question myself. I was wondering, so what you were saying towards the end of your talk, you were saying that it's difficult to find what as machine learners we would call good quality wolof data because the language is mixed with words from other languages.
Yes.
Is this a problem that would be common to other low resources languages? So you mentioned that most African languages are low resources, and do they also share these issues that they would be mixed with words from different languages in the corpuses?
Mm-hmm. Yes, so actually, yeah, I think this is common because I know, like from Africa, this is common because most of us, we do not have our local languages has like how do I say it, the national languages. So we are using some different languages. When you go to school, you will learn French and English maybe. So when you are speaking Wolof, unfortunately, you will add some words coming from English or coming from French. So this is why most of the monolingual data you will see, you will find like words coming from different languages.
Okay, so yeah, I mean, it's of course it makes an additional difficulty, but at least if there are several languages for which this is the case, that means more people interested in working and solving this problem.
Yeah.
And yeah, so any other questions? Or so I had another question still about all the difficulties that are linked to those low resource languages. You highlighted at the beginning of your talk that I mean, the vast majority of languages are low resource languages.
Mm-hmm.
And I was wondering, are you aware of, I'm sure that you're not the only people working on a low resource language, and are you aware of other communities who are working on this type of things, and for other low resource languages, and what would be the differences or similarities with what you're doing? Or
Yes, actually, yeah, we have like the Masakani, maybe, I don't know if you know, but it's a very large community which is using like working on low resources for natural language processing and mostly for machine translation. So this is like, I think this is the biggest community in natural machine translation in Africa, and they are actually doing like very advanced work on this. Yeah.
all right, so this is nice. There's a question also from Mariama. Mariama, maybe you want to ask your question yourself, or otherwise I'll read it.
Okay, so thank you so much for the great presentation. So I was just asking about, like, given that almost all African languages are mixed, like when you are speaking, so do you know about any ongoing works that aims to deal with these mixed languages?
Actually not, because people are just trying to create like more data, like a good parallel corpus, but I don't know any work going on this dealing with the mixed data. Yeah.
Okay, well, I think this is an interesting research question. If you're curious about if you need a new machine learning project, it looks like mixed languages or
Sure, yeah.
are an important topic. All right, so any more questions? We have a bit of time and Azade is still here. So I think if you have questions for Azade, we can also take more questions for her or more questions for Sokhar. There's a few people who are still with us. Starting to be a bit late. Yeah, good question. An additional good question in the chat. So did you need to train a specific tokenizer for wolof?
Okay, I mean, normally, yes, you need to sometimes train your specific tokenizer, but actually the model we're using, the Joy NLP model is coming with the specific tokenizer. So actually we did not train any tokenizer for this case. We just use the tokenizer coming from the Joy NLP models. But I think it's a good idea to train your own tokenizer. Maybe it can improve the performance of the model.
Did you actually look at, did you look at what the tokenizer was doing and were you happy with it, or did you just use it and didn't really look at the...
Yeah, I did look at the tokenizer, how it works and what it's doing. And I find it interesting. So I did not take time to train my own tokenizer. But this can be something to add on.
Okay, maybe another question is, so you were saying at the end that of course because you're training on the Bible, then you have this limitation that you're better about biblical sentences than any other sentences. But is this something you actually observed like in practice, that if you give, did you actually like try giving it random, not random sentences, but sentences for which you knew the translation, and did you observe that it was working better on some sentences than others?
Yes, that is true. I did try and check like what will be the translation if you use different sentences which are not coming from the Bible. And you will see that it's always through finding vocabulary from the Bible, so which means you will have a wrong translation. And this is what is due to the domain mismatch problem.
Okay, I'm assuming it can sometimes give some very weird sentences, even if it keeps the meaning, but if it's using the biblical language.
Exactly, yeah.
All right, well, thank you very much.
Thank you also to you.
So are there any remaining questions for Sokhar, for Azade, or for the WiMLDS team on one side or the other? We still have a few minutes of our time. If not, I will thank you all for being here tonight. Thank you so much, Azade and Sokhar, for giving your talks. Thank you, Sokhar, for keeping calm after you had all those technical issues and completing your talk. It was very interesting. And thank you, everyone, for coming. This is one of the things I find exciting about this pandemic, is that we can have meetups with people in Dakar and talk about science together. So thank you all very much. Have a good evening and stay tuned for further events.
Thank you for the organization and the invitation.
Thank you very much. Bye-bye.
Bye, everyone.
Bye.
Goodbye. Thank you.
Hi, thank you.
Thank you, bye.